I want to talk about what happens when I'm drawing a dot diagram and I don't have enough electrons to complete octets around all the atoms with single bonds. So what I'm going to talk about here is what happens when you have too few electrons. And the example I'm going to use is going to be a nitrate ion. NO3 minus is called the nitrate ion. It's a polyatomic ion. So I'm going to work through those steps that I said before. The first thing I want to do is I want to count the valence electrons. So nitrogen has 5 valence electrons. Oxygen has 6, so there are 3 oxygens, so it's going to be 3 times 6, which is going to be 18 valence electrons. And then because that ion has a negative charge right there, I'm going to add one more electron. So there's another electron that gets added for 1. So when I add these up, my valence electrons, I have 5 plus 18 plus 1. That's going to be 24 valence electrons that I have to use to build this polyatomic ion, to try to figure out its structure. So the first thing I'm going to do is I'm going to draw a skeleton structure of a nitrate ion, taking the clue that the first atom in the structure or the central atom in the structure is written first in the formula. So I'm putting nitrogen in the middle, and I'm going to have an oxygen and an oxygen and an oxygen. And now again, I'm building this molecule sort of in a north, south, east, and west orientation. When we talk about the specific structures, that's going to be become pretty obvious because everything has what's called a tetrahedron basic shape, because that gives you 8 electrons that are oriented around a sphere, and we'll get into all that a little bit later. But so there, I have my skeleton structure. Now my rule is that I'm going to add up the number of bonds that I'm representing, which is 3 bonds, multiply that times 2 because each bond includes 2 electrons. So that's going to equal 6 electrons that I used. Alright, so now I'm going to subtract that amount from there. I end up with 18. So I have 18 left over. So what do I do with those 18 leftovers? Well, the trick here is that I want to place those 18 electrons around this structure in hopes of making everybody have 8 electrons around each other, or around themselves. So here goes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And now when I look at this structure, I go, okay, looks pretty good. Well, there's a problem. The oxygens are great. Every oxygen has 8 electrons around it, but the nitrogen only has 6. Now, what's going to happen is these electrons are mobile, and they're going to move around where they need to. So there is going to be some pair of electrons, and I'll just pick on this pair right here, that is now going to move down into a shared bonding position. And what that's going to do is it's not going to change the number of electrons around the oxygen. The oxygen is still 8, but what it is going to do is help the nitrogen get 8, because now with the double bond, with 2 more electrons down in there, it now has 8 as well. So I'm going to get rid of those electrons up there, and I'm going to place them down in a bonding position. So it looks like that, and that's how we represent a double bond. So the nitrogen has 8 electrons. Change the color to do it, but 2, 4, 6, 8. Each oxygen has 8 electrons. 2, 4, 5, 6, 7, 8. 2, 4, 5, 6, 7. No, I counted wrong. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. Anyway, you get the idea. And the last coup de grace on this is to place this in large brackets representing the fact that it has a negative charge. Okay? Now, one more case. This one happens when I have too many electrons. So now I'm going to talk about the case where I have too many electrons, meaning more electrons than I need to give everybody an octet. And what I'm going to use is I'm going to use this molecule, xenon tetrafluoride. Normally, noble gases don't bond with anything, but the larger ones do. Guy won a Nobel Prize for this making a compound out of a noble gas, and this was it. So again, my rule is count up valence electrons. Xenon has 8. I have 4 fluorines. 4 fluorines at 7 apiece will be 28. So I'm going to end up with 36 valence electrons to deal with. Now what I'm going to do is I'm going to draw that skeleton structure with xenon in the middle because it's written first, and I'm going to put 4 fluorines. Halogens always terminate a chain in a molecule like this, the north, south, east, and west orientation. I'm now going to add up how many of those bonds times 2. So I have 1, 2, 3, 4 bonds represented. So 4 times 2 equals 8. So those are the used up electrons. So it's 36 minus 8. I'm back to 28. I'm not. I'm back to 26. No, 28. Okay, so I got 28 that now are leftovers. So here's what I do. As with everything, I'm going to use those to try to give every molecule or every atom in that molecule 8 electrons. So here goes. I'll start with this fluorine right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Now if I look at that, everybody has an octet around it. The fluorines do, the xenon does, and I use 24 electrons. So I'm going to subtract those 24. This gives me 4 electrons too many. So what I do with those, this is very simple. All I do with those 4 electrons is I place them around the central atom. So I'm going to place them, I'll make them blue, I'm going to place them right there. And what that has done is it has made xenon now happy with 12 electrons around it. So it's called an expanded octet, and it happens sometimes with larger atoms because larger elements have enough protons to hold those electrons in the bonding form. So it happens once in a while, and that's what you do.